of Naples, Federico II, and Kent University in Belgium. So the title of my presentation is a box plot, a spherical box plot, and the idea is to introduce a new tool, an exploratory tool for the analysis of spherical data that we call the spherical box plot. So first of all, I will very quickly recall the original idea of Tukey's box plot for data on a line and the concept of directional data. And then I'll show you how we extended the box plot for data on a line to the circle, and how it is possible to deal with data on ordering data on 2 dimensions. So that's the original idea of Tukey's box plot for data on a line can be extended to the bivariate case in the Euclidean space. And then finally how we move from the box plot on a circle to the box plot on a sphere. So what is a box plot? Very quickly, a very widespread exploratory tool that reveals immediate information about location, skewness, spreads, and far-out values, sometimes called outliers. So basically, what are the key elements to build a box plot are the hinges that sometimes are also called quartiles. So for the way Tukey called them initially was hinges, and basically they are the first and third quartile, and of course the median will be somewhere in between. And then you need a multiplying factor that is used to extend outward the boxes to obtain the fences, so the red lines that you see on the plot, and these fences are then reduced toward the box to the closest observation. And what falls outside will be a far-out value. So the idea here is to extend this tool to directional data. But what are directional data? So directional data are measurement in angles, direction, axis, or rotation in the Euclidean space, and typically these observations can be regarded as unit vectors in 2 dimensions. And in that case it would be data on a circle or in a 3-dimensional space, and in that case we would be talking about spherical data. So fields of applications are many, from biology to astronomy to political sciences. We'll see later a few examples. So the idea is to create box plots for directional data. This is not a very trivial task because we have to deal with the special features of directional data. Let's make an example. So if you take, for example, 5 observations in degrees, 0 degrees, 30, 55, 330, and 345, and you place them on a line, and you try to calculate the median, that will be, of course, 55. But if you present these observations on a circle, you will see that 55 degrees falls outside the distribution, so really on a tail of the distribution. So you can see that ignoring the circularity, so the curvature of the sample space can be very misleading. If you calculate the circular median, that would fall right in the middle, and that will be 0 degrees. So really, statistical analysis of directional data deserves a special care. And this kind of effect is one of the first difficulties that we have to deal with when building a box plot. So the lack of a natural ordering due to the arbitrary choice of the 0 direction and the sense of rotation. So what we did already last year was extend the box plot to circular data. So for that, the first thing we had to do was to find a way to order circular data in such a way that it is independent from the choice of the reference direction and the sense of rotation. That would be by ranking the data from the point antipodal to the median direction, and that way you would have an outer inward ordering. And once you have that, you can build the box as the 50% of most central observations, and then you can extend the circular range of the box outward by a multiplying factor that would be a nonlinear function of the variability, because the multiplying factor has to take into account the curvature of the sample space, as earlier mentioned. So, very quick example here. This is a unimodal distribution from the Science-Q's John Pusey family, and in this case you clearly see how the asymmetry is well captured clockwise compared to, for example, a density estimate. And another example I want to show you very quickly is the extension we made also to axial data. So these are special directional data as well, where the support is between 0 and pi, but the good thing is that we can easily transform them to circular data by multiplying them by 2 and then back transform at the end. I'll go very quickly so that we don't miss the most important part. So after the extension from the box plot on a line to the box plot on the circle, then we asked ourselves, what about 2 dimensions? So on the in the Euclidean space, it is the first issue that you would have as well would be ordering the data. So there is lack of natural ordering. And for that, we can measure the centrality of a point with respect to a distribution using the concept of data depth. So data depth functions assign a depth value that is higher for points that are at the center of the distribution, and lower depth values to tail points, so points that fall outside the distribution. So you can see that the red point is more central compared to the blue point, and in that case the blue point, the red point would get a higher depth value. So the deepest point can also be used as a location parameter. So using this concept, we have to thank Roussel for developing the backplot. That is the extension of the box plot to the bivariate case. But what about the sphere? Well, we can use the concept of data depth as well, but of course that would be an adaptation of the depth functions to the directional setting, so we would be using angular depth functions, but the purpose would be exactly the same. So measure the centrality of a point with respect to the distribution, assign higher depth values to more central points, and lower depth values to tail points. So once you have an ordering of your data on a sphere, then you can start building a box. But then these are the steps, and I'm going to walk you through this pseudo algorithm here with some help of plots, so that it's a bit more straightforward. So let's start from the box. First step, you would rank the data according to an angular depth function. Once you have that, you can build the box as the convex hull on the deepest 50% of data. And the box would be obtained by arc joining the vertices of the convex hull. And you can already mark the median direction. That would be the deepest point according to the angular depth function chosen. Second step would be build the fences. So that would be the extension of the box outward by a multiplying factor. So here it's a little bit more difficult because you need two information. So the first one would be, of course, the distance of each vertex of the box from the median direction. And that distance would need to be extended outward by a multiplying factor. But you also need the bearing, so the direction of travel. So what is the direction toward you have to move from each vertex of the box in order to land on the destination points that would be the vertices of the fence. So once you have the direction of travel and the inflated distance, then you can calculate each vertex of the fence, and again you can arc join these points. Usually the fence is not drawn because what you have to do after you obtain the fence is reduce this fence toward the observations that are closest toward the box. And to do that, that's the last step. You need something like this. I don't know if do you see the mouse on the screen? Okay. So here, to reduce the fences toward the box to the closest observations, what we did was basically join for each vertex of the fences, we would join two consecutive vertices to the point antipodal to the median direction. So that way you would obtain a set of spherical triangles. So what we need to do then is to check for each observation that does not yet belong to the box, if that falls into any of the spherical triangles around the fences. So if a point falls into the spherical triangle, then we would already know that that is a far-out value, and we would take it aside. Okay, so once we finish this process of checking if every observation belongs to any of the spherical triangles outside, then we would know what are the far-out values. And we can take them out for a while, and then we calculate the convex hull of the initial data set diminished of those far-out values. And that would give us exactly the whiskers. And after that, we can, of course, add these far-out values back onto the plot. So there is just one extra complication, which is the control of the extension of this far out, let's say these fences outward from the box, which is that we need to avoid that the fences start to, so the distance when we move along these extensions wraps around. So this is also called the wraparound effect. It's easier to see on a circle, but that happens on a sphere too. So to avoid that, we make sure that the extension outward from the box does not exceed the point antipodal to the median direction. So once you have that, the last thing would be to clean up all these lines and come up with the final plot, which looks a bit like this. So I'll give you some examples. So the first one is a classic example, 1965. So this is about cosmic rays. So observations are arrival directions of cosmic rays. So there are energy signals going toward our planet, and when they hit the atmosphere, they provoke these kind of rays. And it is of interest to see what is the distribution of this arrival direction. So on the left-hand side, you can see the distribution as a raw data plot, and on the right-hand side, the spherical box plots from a suitable perspective. So you can see, for example, here it's a quite symmetric distribution with median directions somewhere around 90 degrees north. And here you can also see that the fences and the whiskers are quite close together, and that there is quite some variability in this distribution. It covers almost a hemisphere. The second example, a little bit recent, more recent, 1987, is about measurements of magnetic remanence in volcanics. So this is about checking what is left of the magnetism that belongs to rocks. And this distribution is a little bit different compared to the previous one. You can see already some asymmetry, and that the difference, for example, between the fence and how it becomes after you reduce it to the more internal observations. So here it's more along the sphere. And again, the median direction is somewhere around the North Pole. Well, it would be 90 degrees north. And let's say the box is quite concentrated. So the 50% of most central observation is concentrated in a relatively small area compared to the spread of the rest of the distribution. The very last example is about seals movements, and this is a more recent example, and this is about mean location, daily mean location of seals in the Pacific Ocean since January 2000 until March of 2019, so this year, and it's from the top project that keeps recording these observations on a daily basis for many species. And here you can see how the distribution is, let's say, it follows a bit the path of the coast, and it is not extremely close to the coast, but it's not in the deep ocean as well, and this is typical of these species. And what is interesting to see also is that how the 50% of most central observations are concentrated in a very small area compared to how the distribution is spread on the sphere. And there are quite some far out values detected as well. So to close, so we've seen how we can extend the box plots to circular data, and how we can use the notion of data depth to extend the box plot to the spherical setting. As the next steps, we will study the multiplying factor behavior, again as a nonlinear function of the variability, and of course we will have to study the choice of the angular depth function. As some of you might have noticed, in the previous example, it was pretty clear we used the angular Mahalanobis depth, but we want to see how the box plot behaves choosing different depth functions. That will be all. Thank you very much for your attention.
Any comments, suggestions? Please.
Thank you.
So you have a question in the first step of the algorithm?
Yeah.
Yes. So in the first step of the algorithm, I think you were computing this spherical convex hull.
Yes.
So I know how to compute the convex hull if I have points in RD. There are lots of implementations, but I was wondering, I mean, what's this spherical convex hull?
Yeah.
If you could provide some details.
Thanks for the
Thanks.
question. So yes, so the spherical convex hull, so it is spherical in the sense that we have to make two adaptations. So the first one, we have to take into account that the distribution can cover more than a concentrated area of the sphere, and to use, so what we use in fact is the Euclidean convex hull, but it is enriched with the center of the sphere. So if you add the point of coordinates 0, 0, 0, that would make sure that when you use a Euclidean convex hull, it detects correctly let's say, the convex hull of the spherical distribution. And the second addition is that when you join your convex hull, you cannot use chords, but you have to stay on the surface of the sphere. So in that case, we would use arcs, in particular the shortest arc between two observations. So that would cover basically the shortest arc on the great circle.
Okay, thank you very much for the clarification.
You're welcome.
Thank you,
Thanks
David,
for
again.
listening.
The second and last speaker of this session is Mr. Grozavu. Please.
Okay, thank you. Okay, so hello everybody. So my name is Mr. Grozavu. So I came from Computer Science Laboratory from Paris 13 University, and I will present today joint work with my colleagues from Paris Descartes University and from Kyoto, from Kobe University, sorry. So the title of my presentation is Topological Stochastic Neighbor Embedding, and actually I'll show a work how we can do clustering and dimensional reduction simultaneously. The outline of my presentation is the next one, so I will start by a small introduction, and then I'll speak about the topological clustering, and then I'll show how we can take advantage from spectral clustering, stochastic neighborhood embedding, and self-organizing maps. And I'll end by some experimentation and some conclusion. So what is clustering? Actually, clustering is, I think everyone knows, it's to group together similar objects, and we have two types of clustering models, hard clustering and soft clustering. And in this work, we are interested in hard clustering. It means that we can have object which belongs only to one cluster. So it's hard clustering model. So what are the problem and the motivation? Actually, one of the problem in clustering is that if you have high dimensionality data, and then you have a lot of variables, the clustering can be very difficult to do because you don't have any supervision. We have also spectral clustering, which works very well for some problematic clustering data. I'll show you in the following. And it was shown that it outperforms the traditional clustering models. One of the problems for the spectral clustering is that the computational time is very high because we have to compute an affinity matrix, and it's very complex when you have very large data sets. This is why we want to take advantage from the topological learning when we will introduce the neighborhood information during the learning process. So what is the topological learning? Actually, we use a self-organizing map. And this slide you have in black points are the data, and green points represent the neurons or cells, which during the learning process will take advantage of the structure of the data, and where we have a more concentrated black points, data, the neurons or cells will detect this information. And the neurons which are in the middle in this image usually have no data, they're empty neurons. So this is how topological learning for using neural networks works, and how we can do it by optimizing this cost function, where we have xi minus wg is the distance between a data point x in input and the prototype of a neuron, weighted by a neighborhood information, which is k here, and k actually is a distance matrix between all the cells of a map. And of course, the size of a map should be fixed by the user, or we can also fix it heuristically by using the size of a data and the size of variables. So it works by minimizing these functions. So actually, the assignment function will be this one, and we find the minimum distance between every point in the input, and W, which is the prototype of a map. And we call this neuron, it's a winding neuron. So it's very close to k-means if you delete this neighborhood information, neighborhood value, you obtain the classical k-means algorithm, but here we have more cells compared to clusters. Okay. So we have another way to do it by using probabilistic models. So it's called generative topographic mapping. So which had the same goal. So Bishop introduced it in '95, but the principle is the next one. We have a latent space in the input, and we have to maximize the probability that this function phi to maximize the probability that the latent space in the input will generate the data space. So actually, this latent space can represent the neurons that we showed before. And the optimization is done by using expectation maximization algorithm. So I don't have time to show the details here. I come back to the difficult clustering problems. I said that sometimes you can have data which is very hard to cluster with classical models. You have an example on this slide. The red points represent the noisy, and the blue points represent some cluster structure. So if you apply classical clustering models on this type of data, usually it is impossible to find the structure or to detect the clusters. This is why we have the spectral clustering, which is works well for this type of problems. And the goal is to construct an undirected graph G with V vertices which represent the points, and E is the edge, I mean the links between the data points. So what you have to do, you have to compute the compute the adjacency matrix W, upper W, between all the points of the data. So it's very complex when you have a lot of data. I mean, more than 5,000 objects. It becomes difficult to compute this matrix. Of course, if you have data already into a graph model, we can easily apply this spectral clustering. Once we computed the adjacency matrix, what we do, we compute the Laplacian graph, and then we find the k eigenvectors of the Laplacian graph, and at the end we apply the k-means model or another clustering model on this Laplacian graph. Also, we can do a normalization Laplacian if you want. So, as I told, this is very expensive from computational point of view, and what we propose also to use the stochastic neighborhood embedding, which is the dimensionality reduction and a projection model in order to transform the data from high-dimensional Euclidean distance space into a small dimensional space. So how it works by computing the conditional probability between the data in the high-dimensional space from data point xg to data point xi. So the conditional probability is the next one, is the first expression, and where delta is the variance of Gaussian that is centered on the point xi. And for the low-dimensional space, we have to compute, we denote the data, projected data by ye and yg here in this expression, and it's computed as follows. So actually what we want to do, we want to have, you have to compute the projection of the data, it's qgi. And how it works by using this cost function. This is stochastic neighborhood embedding, and the Kullback-Leibler divergence is used to measure the faithfulness with this QGI models PGI, because the goal is actually to find out how we can compute the projection in the projection data. So indeed, to use the stochastic neighborhood embedding, we can use student t-distribution with 1 degree of freedom, or we also use another degree of freedom, and it works like actually we change the pairwise similarity QEG and PEG as follows. So the first model we proposed is to actually to decrease the complexity of the spectral clustering by adding one step here, which is first and two, where we compute the pairwise probabilities or affinities PGI. Actually, what we do, we project the data into low-dimensional space. And by projecting the data into low-dimensional space, it allows us to reduce the complexity of the data. And next, what we are doing, actually, we just a moment here. Yes, we compute the agent vectors L on this data, and then we use k-means to cluster the data. Next, once we obtained the projected data, QGI, we compute the prototypes of the neurons W that we have to fix in the input, the size of a map or the size of the network, using self-organizing map algorithm or generative topological mapping on the dimensional I, which was obtained by using student neighborhood embedding model. And next, what we have to do, we have to cluster the map using K. K is fixed also by user, or K is given in the input. Or we can use a hierarchical clustering algorithm if you have more complex data. We have done some experimentations using classical UCI data sets with a different number of observations from 500 to 5,000 with different number of classes. We used labeled data in order to be able to compute the external validation indexes. And what we obtained, you have here the table which shows the results. We compare this classical k-means, classical spectral clustering, and the third is proposed model. The compute accuracy around and Jacquard index. What we can see that usually we can increase the quality of clustering thanks to the projection of the data. Sometimes it remains the same, like here for cancer data set is 85. But what we have also done, I didn't put here, is the complexity time. We decrease a lot the complexity time. When we have more than 2,000 or 3,000 data, the complexity of the computational time, decreased 10 times. I want just to come back to show you the visualization for an MNIST data set where we have 10 classes. If you use, for example, on the left, the classical principal component analysis, you can see that it's very hard to detect visually the classes. We can detect only two, maybe blue and this one. When we apply the student stochastic neighborhood embedding, before to cluster the data, you can see already visually that the clusters can be detected more easily compared to classical PCA. This is why when we introduce these probabilities into the self-organizing map, the accuracy will increase because this is thanks to the projection of the data into a lower dimensional space. So to conclude what I want to say, that we proposed a new topological unsupervised learning model which allowed to cluster large data sets. Why large data sets? Because we increase the complexity of the time. We are able to detect the structure of the data thanks to the projection using stochastic neighborhood embedding, and thanks to the neighborhood information from the self-organizing map. And we usually show that this model improves the quality of the clustering. And what we want to do now, we are working on to apply the inhomogeneous TSNE, but we proposed also this model last year, to adapt this model for different types of data like interval or histogram data, and to apply these models for the multi-view problems. I mean, then we have several subsets or several views of the same distribution of the data. Okay. So, thank you. If you have questions.
Have you any suggestions, questions? No? So we conclude here the session. Thank you, Nestor, and enjoy your conference.
Thank you.
much. Qui? Dici-
Continua senza analizzare.
Qui, col destro.
Sì, e spegni.
Me la puoi passare così ci trasferisco la presentazione?
Ah, la pennetta? Sì, sì. CTRL L semplicemente per andare
Sì,
su...
controlla per
Sì, per...
Ok, bene. Questa è un po' dura. È proprio la pennetta mia, così.
Spacca tutto. Poi di sotto qual era il problema?
Allora, ci hanno lavorato un pochino con gli le cose sono un pochino migliorate, però c'è stata la pausa estiva, non ci siamo ancora
Ma il problema era quello? Poteva essere quello? No. Allora, scusate, c'è il pointer se lo volete utilizzare, se preferite stare avanti invece del sul palco. Ok, avanti e indietro.
E c'è anche il microfono senza filo.
Sì. Io cammino. Anch'io cammino adesso. Non ci riesco.
sto ferma così. Non mi muovo. E quindi niente, non ci siamo rivisti qui, non ti so dire quanto poi impattava, però qualcosa migliorava, ci aveva detto. Ti tengo aggiornato.
No,
Sì.
first, right? My first is presenter. We do one more, sir.
Faccio io, guarda c'è un cladag da qualche parte, esatto, cladag slides, quello là, cavolo lì, stai a posto.
Let's start this session about mixture modeling for complex data. Thank you to all the audience for being here. We have several speakers from different universities. And they're, and they're gonna talk about application of mixture modeling in various contexts. We're gonna see ranking data, complex time-dependent mixed data, and applications of mixture modelings for dependent, for regression type of problems. Okay, our first speaker is Brenda Murphy from University College Dublin. Thank you.
Thank you. So I'm talking about some work that I recently completed with PhD student Keith Murphy. He's just finished his PhD and is looking for a job. So it's called Gaussian parsimonious cluster models with covariance and noise. And the talk is basically, the structure is I'm going to give some motivation. I'm going to talk about a mixture of experts models, which is a way of bringing covariance into mixture models. I'll talk about Gaussian parsimonious cluster models very quickly, but I expect most of the audience know about that. And then I'll talk about the methodology or the software we developed called MoClust. And if you know MClust, it's like a mixture of experts version of MClust. And then I'll have some results and discussion at the end. So quite often when people are doing clustering, they do their cluster analysis based on some outcome variables, and once they form the clustering, they may then look at some covariance to kind of try and understand what the clusters have actually captured. And the covariates are not used quite often in forming mixture of experts model, which I know I've listed in second place, where we develop a model basically for how does the data behave if we knew the value of the covariates and what clusters the observations come from. We would indicate a variable for that. And we build a model for how does the probability of cluster membership depend on the covariates. And that's what mixture of experts does. But there's another approach that's been developed over the years by Salvatore and Grazia and a few other people called the cluster-weighted models, where they develop effectively a joint model for y and x given cluster membership. So when you combine y given x and cluster membership, with a model for how the covariates behave given cluster membership, and then they have a term for the probability of cluster membership. And then they crank the handle of Bayes' theorem to come up with a model for what is the distribution of cluster membership given. In both of these cases, you kind of use Bayes' theorem to find out things about the model, kind of various different conditional properties of the model, like the probability of cluster membership given the covariates and the outcome variable, etc. So there are two different approaches that appear in the literature, and we're going to follow the second one. The main motivation, we have two ways of thinking about two different motivations for the work. One is, can we bring covariates into n-clust? So n-clust is a very well used method for doing model-based clustering based on mixture models, and it would be nice to be able to bring covariates into the model. And that was kind of our original motivation. But while we were doing the work, we also kind of developed a secondary motivation, which is, well, if we bring covariates into n-clust, we then have a regression type method, a regression method for multivariate outcome variables, but it has the n-clust model structure. So you can think of it, so one is bringing n-clust into regression, the other is bringing regression into n-clust. And they're both the same thing, they're both kind of more or less the same thing. But there are two different motivations for doing what we're doing. So, getting into some of the modeling. How do mixture of experts models work? So we have some response variable yi, and we're going to model it as being conditionally following a mixture model if we know the value of x, which are our covariates. So x are our covariates up here. So the distribution of y given x has a mixture form, but where the mixing proportions depend on the covariates, and the component densities also depend on the covariates. Now, this idea has appeared in statistics long before it appeared in machine learning under the name of mixture of experts model. But just to give you some translation between different terminologies, if you haven't seen the mixture of experts models before, what we would call a mixing proportion in statistics, the machine learning people would call a Gaussian network. So that's one terminology. What we would call a component density, so the distribution of y given x, they call it an expert network. And basically, when you combine these Gaussian networks and expert networks into the mixture model, you get what's called a mixture of experts model. So the Gaussian networks tell us how to mix the expert networks together in order to get a prediction. That's how machine learning people think about it. We take a very straightforward functional form for the mixing proportions. We basically assume that the mixing proportions follow effectively a multinomial logistic regression model. So there's a linear combination of covariates. It's plugged into a logistic function, and that gives us the probability of group membership. And depending on the values of beta, the coefficients, a variable increasing might increase the probability of a particular group membership, decrease, or it mightn't change it at all. And we do so basically that's what's going on here. And we just, is there anything else really worth saying here? Not really, except that it's basically the form of how the mixing proportions depend on the covariates is very likely to have in a multinomial logistic regression model. And then for the for the component densities, I should say, we basically assume a multivariate linear regression model for how the outcome variable depends on the covariates. So we've got a multivariate Gaussian where the mean depends on a linear combination of covariates. I didn't say that there. That's the way we're going to put together the model. A few years ago, I was working with Terry Hornby on mixture of experts models, and we kind of considered four special cases of the mixture of experts model. covariates end up not appearing in the model at all, we get back to being having a mixture model. If the covariates only enter the component densities, or the expert networks, we call that an expert network mixture of experts model. So it's really just, that's very like a mixture of regressions model, which would appear a lot in economics in particular. If we have the covariates only entering the mixing proportions, we call that a gating network mixture of experts model. And then when we have the full mixture of experts model, we have the covariates entering the mixing proportions and component densities. And that's two. There are kind of 4 subfamilies. And when we're fitting the model, we're actually going to look at choosing between these 4 subfamilies. We're going to allow the covariates in our mixture of experts model to enter both places, the expert network, gating network, or both, either or both. And a covariate doesn't need to appear in both. So you could have one covariate appearing in an expert network, another appearing in the gating network, and you might have others that appear in both the gating and the expert network. And this differs from, say, the cluster weighted models. The way the cluster weighted models are developed, covariates have to appear in both parts of the model at the same time. And we allow for things like higher order terms and interactions as well. That's possible in our framework. So we're going to basically, for our component densities, we're taking the M-cluster approach, where we assume multivariate Gaussians, where the covariance matrix has an eigenvalue decomposition of the form lambda DAD. Lambda controls the volume, D controls the orientation, and A controls the shape of the scatter of the points in each cluster. And I'm assuming that people have seen the M-plus models in the past. But say, for example, the EVV model assumes that all the groups have equal volume, but they have variable shape and orientation, as an example. When we go to fit our mixture of experts model, so we end up having a likelihood function that is this form. It's the product of the sum of these mixing proportions that depend on some or all of the covariates, and then these Gaussian terms where the mean depends on some or all of the covariates. And it looks a bit messy, and we use an EM algorithm to fit the model, and we use Aitken acceleration to decide convergence. When we do the EM algorithm, and we introduce the latent Z variable as a latent variable, the E step of the model is actually very like the E step for a mixture model. You're basically working out what's the probability an observation belongs to group G, how it depends on the covariates, component density, again, it depends on the covariates, and then you're just normalizing to get your probability. So it's pretty much the same. The only difference is each observation has potentially got its own mixing proportion because of the covariates, and likewise, the component density parameters might be different for each observation. When you come to the M step, I'm sorry, my clicker isn't working here a second. No, it'll probably flick 20 times. Use the keyboard to move. So that's oh. The mouse is working, but nothing else. Oh, there's loads of stuff jumped. Yes, let's see. Yeah, this is for the M step. It actually works out quite nicely. The M step has 2 terms. The term involving the mixing proportions is actually functionally pretty much the exact same as the likelihood you would have if you were doing a multinomial logistic regression. The only difference is the Z's aren't binary, they're kind of probabilities. But actually, it's mathematically it's the exact same form. And the M step for the estimating the mixing proportions of the expert networks is actually the same as you would have if you were just doing a standard EM algorithm for a mixture model. So the M step breaks into 2 parts, and they're actually both in quite a nice form. Now, this is slightly more complicated, this term involving the estimating this, because we have covariates here, but it's actually very like fitting a mixture of regressions model. So for each observation, there's some probability of following a multivariate regression model, and basically the likeness of the form of that. We found a nice trick basically that you can can estimate the regression part of the model very straightforwardly. When you're fitting a multivariate regression model, the value of the covariance matrix doesn't really come into the calculation at all. So when you're maximizing this likelihood to estimate the regression parameters, the value of sigma doesn't really come into play at all. So when you're trying to optimize this function with respect to the regression parameters and the covariance matrices, if you do the regression first and you compute the residuals that you get, then when you're trying to estimate sigma, you have a term like this, which is actually very like fitting a mixture of Gaussians where all of the observations have mean 0, and you can do that very straightforwardly. We found that actually if you set up your data in a very particular form, you set up this matrix of residuals for each of the G regressions, one for each component, and you set up a Z matrix that has this kind of very sparse form where you take the probabilities of this. You can actually do it very straightforwardly using the exact same M step as you would have for fitting a mixture regression, or a mixture model. We looked at using BIC and ICL for model selection, and we found they both work quite well. And then for searching for the best model for the data, we used a stepwise regression approach, basically. Forward stepwise we found better, especially when you have very few covariates that are actually going to be relevant. An example of our methodology, we took the Australian Institute of Sports data, we took the measurements that were to do with blood as the response variable, so things like red cell count, white cell count, hemoglobin, and iron, and then we took all of the other covariates as potential covariates in our model. So we want to cluster the data on the basis of the blood measurements and have the covariates explain the clusters we got. There's a lot of possible models. I'll just kind of skip over this, but basically, potentially if we did an exhaustive search over all possible places for covariates to enter, all possible n plus models, etc., lots of different numbers of groups, we would actually have over 2,000 models to fit. We actually did that, and we found that the best model for the data is if you use BIC, it's a 2-cluster model. EVE is the covariance structure. We have that the gating network parameters, so the mixing proportions are equal across the groups, which isn't that surprising with the AIS data. And gender or sex comes into the covariance in the model in the mixing proportions. And ICL chooses a slightly different model where it has BMI and sex as a covariate for the mixing proportions, nothing in the expert, 3 clusters, and the covariance structure. The reason we did that was we wanted to see how does that compare to our stepwise algorithm. Our stepwise algorithm found the same results as the exhaustive search, which is good. When we were working on the model, we also thought about the noise component, which N+ has, and I know that Christian and Pietro have worked a lot on. We decided that for some problems where you're doing this, it'd be worth adding a noise component. So a uniform distribution on the space that the response variable takes. We did toy with how the noise component should enter the model. In one case we had the probability of the noise depends on the covariates, and in another case we had that it didn't. It's fixed proportion of the data is noise. One we called the gating, or the gating noise model and the NGN model. I can't remember exactly what these were. And then one option is we don't have noise basically at all, which is all the models I've already talked about. When we reanalyzed the AIS data, we actually found that with the noise component out of the model, we actually found that it did select that you should have a noise component in your model. And it suggested that it's a fixed proportion of the data is noise. And that's just to capture unusual observations that your model is finding hard to actually capture in the clusters. So the model we found was the 2 clusters EEE model. We've a fixed proportion of noise, so the noise probability doesn't depend on covariates. And skinfold, sum of skinfolds and height tell you something about the probability you belong to a particular cluster. And again, like the previous model, sex is coming up as a covariate in the expert universe. These are the parameters of the model, which are quite hard to look at, basically, but we have, that's the parameters find, for example, from the gating network that the model has, if you have a high skin sum of skin folds, which is a proxy for body fat, you're more likely to belong to cluster 2 than cluster 1. And if you're tall, your height is tall, it decreases your probability of belonging to cluster 2. So cluster 2 tend to be people with higher body fat and they're shorter, and cluster 1 tend to be people with lower skin fold thickness and height. I'm sorry, they're taller. Sorry. And a fixed proportion of the data, as I said, is noticed. We have a plot for trying to summarize the results of the model. It's not perfect, but we're trying to, it's using the generalized pairs plot that was developed a few years ago. It's like a pairs plot, but there's different options of some of the variables or covariates. So, what have we done as a result of all this and the demonstration I talked about? We've taken the M plus family of models and we have brought covariates into them. And that can help us understand the structure we got. So for example, for the AIS data, the blood measurements for the athletes seem to fall into 2 clusters. Within each cluster, there's a gender difference. And then the covariates are telling us something about what clusters we belong to. So we found the skin fold, some skin folds and height were telling us we're more likely to belong to one cluster than the other, and likewise and height was telling us that too. So we have now got MoClust, which is a way of basically including covariates into MClust. Another way of looking at what we've achieved too, though, is we've actually developed a mixture of regressions model now with multivariate outcomes, where within each component we're allowing quite general covariate structures like the MClust ones. So that's another useful kind of use of the methodology we've developed. Some future work. We're looking over a lot of models when we're applying MoClust. So maybe actually parallelizing that a bit. At the moment we're quite taking a while with this. Allowing regularization as a way of doing variable selection. There was a talk earlier in the week that people were looking at on that. Maybe allowing for more non-parametric structure for the gating network. We've basically just used multinomial logistic regression. And basically allowing for other structures. So we just assume the input structures, but if you have a high dimensional outcome variable, maybe you want to mix your factor analyzers, heavy tails, you might want to use a different distribution as well. There's an OR package called MoClust that's up in CRAN, and recently accepted as a paper in advances of data analysis and classification describing this work, including all the stuff like the noise control, etc. So, thank you very much.
So, is there any question or comment for time for a couple? One you might.
You may just throw away a remark about the variance matrix not coming into play.
Yeah.
That's true of all the X's the same.
Yes.
Yeah.
Yeah, that's only true of that case, yes.
So you didn't do model selection in any of this selecting. I mean, you didn't drop terms in the regression model.
Not through the fit. In the fitting, so I'm trying to think, yes, no, I remember this. Yeah. We did worry about the issue you're mentioning about make sure we didn't do the wrong thing. Yeah. So when we have a particular model with a set of Y's, X's, and fitting a mixture, so when you're finding the regression slopes, yeah, covariance doesn't come into play.
Provided it's the same X's for each one.
Yes. Yeah, we made that assumption. Yeah, we made that assumption, yes. Yes. Yeah. Yeah.
So if
But then we did do model select. We looked at lots of models that have different covariance.
Yes.
Yeah, over time, yes.
but all
Yeah.
the same set.
Yeah, no, yeah, that's the thing, yeah. Each Y depends on the same covariance, yes, we made that assumption.
I have no idea what happens, but you have to estimate the covariance matrix, which has quite a high cost compared to.
Yeah. Yeah, but we did make that assumption, yeah. It actually came up in the review, somebody just checked we were doing that right as well. So, but I remember, yeah, but yeah. Yes, that's true.
Yes, so basically you mentioned that I was interested in the noise component, and also
Yeah.
when
x have some quite strong influence on the y, the support of the y can depend on x actually quite strongly. And of course, if you don't let the v depend on x, you won't capture that. Now, I don't know how bad that actually is, and I didn't have a solution to this problem, but I think it's kind of worthwhile thinking also what can be done about the value of the density then.
That's true, because we just basically, well, in the univariate case, we effectively took the range of the observed voices.
Yeah, which is kind of, I mean, if you
Which,
you
as
make
if it's
some
very
pictures,
strong relationship, that's very bad.
you get a too big V.
Yeah, if V is too big, and then basically you're never going to cause something noise because the density is too low. That is true, and it's more complex in a multivariate setting.
Well, you're searching over a lot of models, 2,500. Have you looked at possible selection bias in results?
Not really, no.
Other questions or comments?
Curiosity and then a question. In the previous version of class, you had to specify, if I'm getting right, you had to specify the value of V, initialize it, or
Whether you chose, I think you initialized which observations you thought were noise,
Well, if I understood properly, in this new version, even though it's not a new version of class, there you have to specify the proportion of outlying observations, and these are accommodating noise component. Am I right?
Well, you at least give an initial guess, Like the proportion of outliers is estimated.
Okay.
The way we estimate V, we have a few options. We take the smallest rectangle that covers all the data, the smallest ellipse that covers all the data, and the convex hull of the data. And we look at all three of those to choose V, basically. But that's not necessarily optimal. This is the work, say, Christian's doing with Pietro over the years. That is not the maximum likely estimate of V at all. Estimating V is quite messy. So it's almost chosen a priori from the data. It's chosen from the data and just fixed at the start.
Okay.
We take the smallest of those three values, by the way. That's our choice. Thanks.
Riesco a fare questo.
Okay. So our next speaker today is from La Sapienza.
Good morning. First of all, I want to thank again Michael for his kind invitation. Today I'm going to present a joint work with Luca Tardella dealing with the Bayesian mixture of extended Plaget-Luce model to analyze the unobserved heterogeneity of ranking data. Ranking data are common in many areas of research, specifically in those experiments when a sample of n people is asked to rank a finite set of items according to a certain criterion, typically a preference criterion. Some examples are behavioral and psychological studies, marketing surveys, and also, of course, the sport context, where a ranking of the competitors, teams or players, is typically available. Formally, a ranking phi is a Bejettin mapping from the finite set of items, capital I, into the finite set of ranks, capital R, which are both identified with the first k integers. So, the result of the mapping can be represented with a vector pi of length capital K, where the generic component pi I denotes the position attributed to the ith item. This data admit also an alternative equivalent representation in terms of orderings. And ordering pi minus 1 is simply the inverse mapping. So in the generic component of pi minus 1j, we can observe the item ranked in the j position. This means that ranking data are multivariate, characterized by a specific dependent structure, and take values in the finite discrete space of the factorial k permutations of the first k integers. The starting point of our proposal is the Plaquetrus model. The Plaquetrus model is one of the most successfully applied models in the family of the stage-wise ranking models. The Plaquetrus is parameterized by the support parameters, which are positive quantities associated to each item, indicating a measure of liking for each item. This is the formal expression for the Plaquetrus, where we can see that the support parameters indicate the probability for each item to be ranked in the first position, and essentially the model is the analog of a sampling of the items without replacement in order of preference. The underlying assumption is the forward order assumption, meaning that the positions are sequentially attributed from the first one, the top position, to the last one, so the bottom position. In our work of the 2014, we extended this model. We relaxed this assumption by introducing an additional parameter, the reference order. The reference order is in turn a permutation, ρ, denoting the order of position attribution. So the generic entry ρ, ρt, denotes the position attributed at the stage T of the ranking process. If we combine the ordering π-1 with the reference order, we obtain the list eta-1, listing the item in order of selection at the different stages. So, thanks to the additional parameter, we extended the Plaquetrus model in the extended Plaquetrus model, shortly EPL. And in this case, the support parameters indicate are proportional to the probability for each item to be selected at the first stage of the ranking process, and hence to receive the position indicated in the first entry of the reference order. This means that under this model specification, the two parameters are linked to each other because the meaning of the support parameters depends on the other parameter. So we originally proposed this model and its finite mixture extension and solved the inference from the frequencies perspective, specifically by constructing an appropriate EM algorithm. And recently, in our work of the 2019, we considered the Plaquetrus model, the extended Plaquetrus model in the Bayesian framework. Substantially, we solved the inference by combining two strategies. The data augmentation by adding the latent quantitative variables y's, which are introduced in order to make the inferential problem analytically tractable, and which are assumed with a specific conditional posterior distribution, combined with the prior specification characterized by prior independence and by a partial conjugate structure, because we adopted gamma densities for the support parameters, which are conjugate with the EPL. So in order to gain further flexibility of our model and to provide a tool in order to investigate the group structure of ranking data, we now propose to extend this Bayesian framework into the finite mixture context. So our proposal is to extend this combination, these strategies in this way. In this setting, we have, first of all, to combine two sets of latent variables, the latent variables y's, which I've just seen, with the latent group structure zetas. And substantially, we considered this extension for the posterior conditional distribution, which will be substantially the full conditional used in the MCMC algorithm. Then we generalize the prior specification by adding the prior on the mixture weights, which is a traditional Dirichlet distribution. So this is the generic outline of the MC algorithm that we use to sample from the posterior distribution. And essentially, we will see that this is a tune Metropolis Hastings within Gibbs sampling algorithm. Specifically, the mixture weights the latent quantitative variables wise, the support parameters and the latent group memberships are sampled from their full conditional distribution. This is because this is due to the partial conjugate structure, so we have a straightforward update of their prior distribution. The main novelty concerns the sample step for the component-specific reference order. And I'm going to provide more details on these steps. These steps substantially combines two metropolis hastings. First of all, the first metropolis hasting step is based on a joint proposal distribution. This is because we need to link the simulation of the reference order with the support parameters because, as we have seen, the two parameters are linked to each other. So we consider this joint proposal distribution with this specific dependent structure. We first simulate the first entry of the reference order, then we simulate the entire vector of support parameter conditionally on the drawn value for the first entry of ρ, and then we sequentially sample the remaining entries of the permutation ρ. So to sample the first component of the reference order for the generic component, mixture component G, we consider a multinomial distribution over the capital K position, which are all available at the first stage of the ranking process to be assigned. And for this first step, we consider a discrete uniform distribution on the capital K positions. Then we sampled the support parameters conditionally on ρ1 from a Dirichlet distribution. The shape parameters of this Dirichlet distribution are given by the product of alpha 0, which is a tuning constant, multiplied by R, which is the vector of observed frequencies that the items are ranked in the position indicated by the first entry of the reference order. So, of course, these quantities are computed for each subsample of units which are assigned to each component. Then we have to draw the remaining entry of the reference order, and for the generic stage of the process, stage T, we performed these steps. First of all, we computed the contingency table, obtain which has as the two margins the observed distribution that the items are ranked in the position indicated assigned at the previous T-1 stage of the ranking process, with the number of times that each item is placed in the positions which are still available at stage T to be assigned. Then we compare this contingency table with the expected frequencies, contingency table obtained with a Monte Carlo approximation. We compared observed and expected frequencies by computing this distance. Then we scale this distance in order to ensure unit sum. And then before defining the multinomial distribution to simulate the generic position attributed at stage T, we reallocate the distance to the positions available at stage T by considering the reverse order. Then we add a tuning constant h in order to avoid a two-sparse distribution. We rescale this quantity and we consider this quantity in the multinomial distribution to select the generic component of ρ. Okay, so in this way we obtain ρ tilde, p tilde, which are the proposed value, the proposed pair of the reference order and of the support parameters, and we apply the standard acceptance rejection rule for the metropolis hastings. We obtain in this way ρ prime p prime, which has to be regarded as a temporary drawing for the parameters, because In order to try to accelerate the mixing of our MCMC algorithm, at this step we propose a further metropolisasting step. So we propose a further value of rho in order to favor local moves with respect to rho prime. And this new proposal is obtained by randomly swapping two consecutive entries of rho. Then we reapply the acceptance rejection rule for the metropolisastings, and in this way we obtain the actual drawing at the generic iteration of the MCMC algorithm for the reference order. So we first check, of course, the ability of our MCMC algorithm to recover the true parameter values in a simulation study, and then we apply this method to a real data example. The real data is the game data, which is included in the mLogit package. It's a dataset including 91 complete orderings of 6 gaming platforms, which are illustrated at the top of this slide and labeled from 1 to 6 in this order. So we fit it to this data mixture of Bayesian mixture of EPL with a number of components varying between 1 and 6 by adopting a weakly informative prior scenario. We launched the tuned metropolisastings with the Gibbs sampling algorithm by initializing it with the maximum likelihood estimates. We considered 15,000 iterations and discarded the first 5,000 as burning phase. We also performed a comparison with the Bayesian mixture of distance-based model by adopting the Kendall distance as the metric of the permutation space by using the function included in the Bayes-Mallows package. Here in this plot we have the DIC for the two mixtures. In orange we have the DIC for the EPL mixture, and in green for the distance-based. As we can observe, essentially the minimum values of the DIC are very close to each other for the two mixtures. But with our mixture of EPL, we essentially obtain a more parsimonious solution. And so since for G equal to 2 and 3 we obtain very similar values, I'm going to provide the results for the two-component mixture. But before doing that, I have to stress that we are in a mixture context. So we cannot straightforwardly analyze the MCMC output because we have in this case, two sources of multimodality. The first one is the one induced by the label switching problem, because we know that in a mixture we have an arbitrary labeling of the mixture components. So essentially we have the classical unidentifiability issue of a mixture. Then we have another source of multimodality due to the fact that each EPL distribution is characterized by the link between rho and P. So since the meaning of the support parameters depend on the reference order, essentially an EPL distribution can be regarded in turn as a mixture of placket-loose distribution where the components are substantially represented by the reference order. So we have to substantially adjust the raw MCMC output in order to derive meaningful estimates of the EPL parameters. And we propose this sequential strategy. We first remove the label switching problem by adopting a relabeling algorithm, the pivotal reordering algorithm, and then for each mixture component, we derive meaningful estimate for the support parameters by conditioning the drawings of the support parameters to the maximum a posteriori estimate of the reference order. So these are some results. At the top of this slide, we can see the bar plot, the posterior distribution for the reference holder of the two mixture components. For the first mixture component, we have essentially a distribution concentrated on the backward order. And for the minor mixture component, the second one, we have a more diffuse posterior distribution, specifically on sequences which are characterized, this is the map estimate, by an alternating path, by an alternating attribution between top and bottom position. And at the bottom of this slide, we can see substantially the estimated modal ordering of the k items in the two mixture components. To conclude, I am introduced a Bayesian model of a Bayesian mixture of EPL models, and this can be regarded as a generalization of two models that we have already proposed in the literature. Specifically the frequentist mixture of EPL and also the Bayesian mixture of traditional Plaget-Luce by adding the inference on the reference order. We solve the inference by constructing a tuned metropolis hustling with the Gibbs sampling algorithm, and we discuss also the issues related to the analysis of the MCMC output of our algorithm. And I presented also an application to a real data set. For the future, first of all, we would like to include this method in our PL mix package. The PL mix package is available on CRAN. We wrote this package that implements the Bayesian mixture of traditional Plaget-Luce models. So we want to add substantially the estimation steps for the reference order. We would like to further enrich our analysis to account for example, accounting also for the presence of partial observations and for the availability of individual or atom-specific covariates. So thank you very much for your attention. Yes, it is characterized essentially by the same unidentifiability issue of a standard Plaget-Luce, which is substantially the unidentifiability up to a multiplication for a positive constant of the support parameters. But it's essentially the same.
Was the solution with two components much different from the solution with three components?
No, it's not so different. With the three component, it's added just a minor component with a very low weight, equal to 0.05, and I prefer to not show that solution because it is very small, that cluster. So I don't think that it's so representative. It's so good, the estimation of that small component. The other two mixture components are essentially the same with the two solutions that I have already shown. Yes, but maybe I don't understand your comment.
You have to fit a model every time you fix a number of components in order to calculate the DSC. I was just wondering if you...
Just one model, and the DSC is computed on the different iteration of the MCMC algorithm.
Yeah.
Okay.
Yeah, but just
Yes, yes, you have to fit. Yes, yes, it's true. Currently, the code is not optimized. The major problem with this, with the implementation is the computation of the likelihood, because you have essentially the fact that your data are, first of all, multivariate, and with the EPL, you have also the dependence, the update at each iteration of the reference order, which is in turn a permutation. So, in this sense, yes, it's computational intensive. We would like to involve this algorithm in the PL-Mix package, in particular to optimize this code, because for the package we have overcome this issue by implementing, for example, the likelihood, some specific steps of this algorithm with C++. Okay, so in this sense we can solve your comment.
Sembra che non trovo. Proprio il mouse. Mi piace. Ho deciso di dire così. Ecco così, ecco. Chiedo Acrobat e lo faccio divertire. Vediamo se così va. Direi che è andato, no?
Okay, our next speaker is
Thank you, Michael, for the invitation. This is a joint work with Roberto Rocce e Moria Ranaldi from Sapienza, and it's motivated by the analysis of a longitudinal multivariate data set coming from a Chinese longitudinal data set on elderly people. In this data set, we have several variables which are of different types or mixed type longitudinal data. And we are proposing a model which is able to analyze jointly several data features. And well, the outline of the talk seems to be quite long, but I'm going to skip probably some of the details. But of course, well, the starting point is why should we introduce another model to deal with this kind of data? When we analyze longitudinal data, we have to take into account that there are several data features that must be taken into account and modeled properly. Mainly the dependence over time, so the correlation between multiple observations belonging to the same unit, heterogeneity that might arise in our population, so the idea is that we have subpopulations in our samples, and likely we might have correlation between multivariate variables. In this case, we have also other issues that we have to account for, and the issues are related to the nature of the variable. The fact that we have not only continuous variables but also categorical ones may cause a problem. Because when we would like to analyze to consider a joint model, taking into account all the informations coming from the variables, usually in whatever clustering setting, we assume some sort of conditional independence given covariates, given latent variables. What we are going to do instead is to consider really the joint distribution of continuous and ordinal variables in a single model. Another issue that we might have is that when we consider several variables which measure pretty much the same things, like health conditions or food habits or whatever, they share exactly the same latent structure. I eat only meat. So if I have to analyze my food habits, well, probably if you look at how much fruit, vegetables, and ice cream I eat, means nothing. So why should we consider all these variables in the model while we can collapse them considering simply sort of combination So we might have some variables that do not bring with them the clustering structure that we may observe in the data. What else? Well, when we deal with ordinal data, there are several approaches to deal with ordinal data. In this case, we are going to consider what is called underlying response variable approach. This is just, well, this is a very nice approach because it allows us to consider easily the joint distribution of ordinal and continuous variables. A lot of words on this slide. This is pretty much the main contribution. How do we deal with all these features in a single framework? Well, to analyze the clustering structure of the longitudinal data, which is likely to vary over time, we consider what is called the Markov model. So simply a mixture whose components may vary over time. So a subject, an individual, a unit may change component over time. So it's not much different from a mixture model. In this context, in this framework, we introduce some sort of factorial model to distinguish between informative and uninformative dimensions, trying to identify the variables which are not really interesting from a clustering perspective. So we are able to define some informative and uninformative dimensions from the factorial model. In some sense, the model is parsimonious, as I was saying, because one of the aims is to reduce the dimensionality of the problem. As usual, when you would like to account for multiple data features in a single framework, you might have some computational issues. And in this case, the computational issues are related to the estimation of the parameters, which may be cumbersome if you would like to use a full maximum likelihood approach. So to overtake such a problem, to speed up the algorithm, honestly, and not only this, but we will see it in simulation, we consider composite likelihood approach. Just the main ingredients of our modeling, we have some x or ordinal variables and some y continuous variables. The number of categories between the ordinal variables may change, so they must not be fixed. In one category of web variable, we might have 3 categories, in another one, fine, it's not a problem at all. The main assumption is, well, this is crucial. The ordinal variables are considered as a categorization of a continuous multivariate latent variable. This is the approach of the URV approach I was talking before, and these allow us to consider the multivariate Gaussian distribution as our reference distribution. To deal with time, with the time dimension of the longitudinal data set, we simply assume the first order finite state Markov chain. So nothing really. This is another crucial point of the modeling. So how do we relate the categories? So the categorical variables with the continuous ones, we have some sort of thresholding model. These thresholds are quite important because if we have to reflect with the threshold approach the latent structure, the presence of subpopulations. In some cases, when these thresholds are not well estimated, or the problem might be that you are masking the existence of a clustering structure in the data. Using this approach, then it's rather simple because at the end what we have is a multivariate Gaussian distribution as a conditional distribution. So we have a multivariate hidden Markov models in which we consider also dimensionality reduction to account for the presence of important, let's say, informative and non-informative variables. The dimensionality reduction, as I was saying, is pretty much based on the existence of the specification of a factorial model. So we simply link our response variable to some latent factors, and this link is matched by this matrix A. The idea is that we might have some factors that contain the informations about the clustering and some others which are considered as missing. This is pretty much how it works in practice. The specification of our factorial model. So we simply have some factors that are informative and some others that are was saying, when we would like to account for several data features, usually the problem is in the computational boundary required to estimate the parameters. At first glance, if we look at the likelihood function, it doesn't look so weird because in principle this is a mixture model. So these are the weights and this is the conditional distribution. Bearing in mind that these are not only weights, this is a Markov chain. Well, the model is a little bit more complex, but standard techniques are available, so it's not a problem in principle. Because when we consider the form of our multivariate distribution, then we notice that the part related to the ordinal variables, given the continuous ones, have this quite complex form, which involves several integrals. When we have to deal with several integrals, we might have computational problems. So instead of considering the full likelihood approach, we prefer to generate some sort of surrogate functions. Which is the role of these surrogate functions? The role is to simplify the computation. So instead of considering the entire distribution of the categorical variables, we consider the pairwise distributions of categorical variables given all the continuous variables times the probability density function of the multivariate Directional distribution for the continuous variables. In this way, using all these pairwise sub-likelihoods, we strongly simplify the algorithm and speed up the algorithm. It's a robust method, and the estimators are being proved to be consistent, so we are not losing much information. Maybe I will show you then exactly what's the effect of using this algorithm in practice. So as you will see, it works very well, so it's not a problem. Again, this is how a complete data log likelihood looks like. So at first glance, it's not so difficult to deal with. The tough part relates here. As you see, we have to maximize this part of the complete expected value of the complete data log likelihood with respect to I and J, where I and J are two different categorical variables. So we are taking all the pairs, conditionally all the continuous variables. So, and again, in the composite EM algorithm, when we refer to the latent part of the model, so the probability of starting in state K can be easily solved. The transition probability matrix of the Markov chain is just a solution of this equation. There are closed form solutions, so they're quite standard. It's not a problem. What is a little bit more complicated is the estimation of the parameters related to our manifest distribution, so multivariate distribution. As you see here, the posterior probability of belonging to state K at time t is different for each pair of categorical variables. So this is where the computation becomes a little bit slow. But indeed, this is useful. As I was saying, there are closed form solutions for the latent Markov, the Markov parameters, so the probability of starting in state K and the transition probability matrix. There are no closed solutions for the other parameters. So what we have thought is simply to consider some sort of hybrid EM algorithm and use some numerical optimization for that part of the algorithm. When you use numerical maximization, these kind of algorithms, it's important to define proper initial values. Otherwise, the algorithm will do pretty much mess. One of the aim of this approach is to see if there is a clustering structure in the data that varies over time. And the classification here is pretty, it's not as usual, simply because don't forget that we have to consider some sub-likelihoods. And the fit of each observation on which then is based the probability of belonging to a single state is obtained by multiplying the corresponding sub-likelihoods. So in some sense, we have to define a degree of membership which lies between 0 and 1, so we normalize these values. And the other problem is model selection. Here I'm showing you one of the criteria we have used, and it's based. This is a criterion, as you see, is based just on the penalization in entropy. So we are looking just at the classification. This is not the only one we have considered. We have also considered cross-validation, which is time-consuming, but seems to be better than this one on simulations, but in the empirical applications, they provide exactly the same results, so this is easier to be capturing from a slide. So I prefer just to show you that we do model selection using a simple criterion based on classification. Okay. Simulation, this is just the setting. So we consider different settings, so varying the number of longitudinal observations, varying the number of times on which each observation is observed. We vary also the level of overlap between the different conditional distributions, R and low. And then compare the classifications in terms of the adjusted rand index. So, we have not considered only our model, which is in this graph called simultaneous clustering and reduction HMM in the Markov models, which, as you see, performs quite well over all under all scenarios. And we compare this approach with similar models. One is called naive HMM, in which the categorical variables are considered continuous. So we consider, instead of having categorical variables, we assume that our categorical variables are Gaussian. And the HMM, in which we account for the fact that the variables are categorical, but we didn't perform the dimensionality reduction, so the information of the classification from the information contained by noise variables is also taken into account for the classification, and the results, as you see, are quite bad. So it seems that to account for all the data feature, especially when there is high separation between the conditional distributions, is well recovered by our model. And just the example. So these are the variables we are looking at. At first glance, our idea is just to check how these old people health behave, how it changes over time. So we think, okay, which variables we might consider? For sure, we can see their quality of life, self-reported quality of life and health. Then they look at their food habits, and then they also would like to see some, let's say, objective measures like the weight, systolic and diastolic blood pressure, just to see if they have some health issues that might be recognized by these quantitative variables. As you can see, the number of categories may vary. If I remember well, fruit has just 4, while the others have 5 categories. It's not a problem, as I was saying. The order of the categories is important to understand the results. So if you look at the way the categories are ordered, very good. So the best one, let's say, are the first was the first one, and rarely or never or very bad the last one. Model selection. As I was saying here, we use the CLC criterion, but if we look at the cross-validation, the results are pretty much the same. So we have 3 states, and sorry, this should be K, but anyway, and 2 factors. As you see, we have run models with different numbers of states and different numbers of latent factors. This slide is just to show you that there is some sort of variation over time, so it's very likely that these people change states. And okay, and then we have to interpret somehow our results. And the type of results we obtain are of 2 different kinds. First of all, we would like to see which are the most relevant variables for our classification. So this is the percentage of the variance explained by the, let's say, informative factors. In this case, it's just 1. And this is the percentage of variables explained by non-informative factors. There should be some bar over the Q here, which is not really visible. So for sure, it seems that there are some variables strongly related with these factors. Well, and some others are clearly not related to informative factors, so they do not contribute to our classification. This can be also seen by looking at the estimated group state-specific means. As you see for the last three variables, which are not related to the informative factor, the means are pretty much the same. So they do not really contribute to the classification. On the other hand, for example, fish, here you can see some differences between state-specific means. According to this standardized means, we can also give a physical meaning to the states. So sometimes all these computational and quite complex modeling are just used to account for data features, but the states might or might not have a physical meaning. In this case, they have a physical meaning. For example, the state number 2 is characterized by a specific behavior with respect of all the food variables. State number 1 is characterized by the variables on how do you feel, so anxious, lonely, useless with age. And state number 3, in some sense, is the good state. So if we have time, we can go back to that. But imagine that these people are very old. They are 90 and above. So even if they start in state 3, it's very likely that they go worse and worse. This is what we do. Just to conclude some remarks, of course, this is not the first attempt to include dimensionality reduction in a hidden Markov model, but this is a parsimonious way of doing it. There are several other approaches that can be used, but we think that in modeling all the features in a single framework in this way is simple, computationally fast, and produce results that are comparable with other existing approaches. Thank you.
Questions or comments for Antonello? I have one. Coming back to the estimated means, these are on the scale of the latent variable, right?
These are standardized. Yeah.
Is there a way to map these parameter values to the original scales, especially for the ordinal variables?
Well, for the ordinal variables, we have other estimates. There was so the fitted percent frequencies of each category in each state. So we can go back to that just to know exactly which are the estimates of the estimated frequencies for each category in each state for each categorical variable, which is also something we are looking at. But the table would be then huge to be shown by this. We can look at this.
Other I have another one. We might need to discuss later about that. But often when looking at mixed data, the problem is modeling dependence, okay, between different types of variables. You don't show estimates for the latent, for the covariance matrix of the latent variables. Do you see something happening there, especially for this data, or?
What do you mean with something? Well, the idea of using.
Interesting pattern, or?
Honestly, I don't remember.
Or
Yeah, but yes. The idea here is just to use this URV approach to consider the joint distribution of all the variables instead of assuming conditional independence. So with this principle, we can observe estimate correlations between category and continuous variables. Yeah, these huge covariance matrices. Yes.
So it's more a computational trick. You're not that interested on modeling or interpreting the actual dependence.
Well, in some sense, we are doing this with a factorial model because we are reducing the dimensionality reduction of the problem. So we are looking for variables that share some common features.
Okay, so let's give another round of now the coffee break. Your USB key here and put the slide somewhere.
check all of them. Go ahead.
Devi metterlo qua. Certo, conviene. Stiamo facendo questo navolo tutto massimo la sorgente. Ce l'hai qua.
Ma c'è una cartellina per la sessione o li metti così sul testo?
No, magari fai una cartellina. Falla tu perché se no dopo arriva questo qua della...
Dimmi come lo chiamiamo.
Chiamala semiparametrica.
Oggi è il 13.
Ora cambio nome così ci metto Rampi.
Sì,
Se no, perché se no poi non capiamo.
Ci vuole un attimo.
Sembra tranquillo. È perché c'è solo USB-C. No, ce n'è 4.
La mia penna così.
Ci vuole uno per la S, uno per la
Almeno siamo pronti.
Esatto, sì.
Saremo sicuramente in ritardo.
Kingston.
Kingston.
Certo.
Non riesci a vedere. Andiamo a vedere sul desktop, intanto il primo.
Lettura c'è, Coffee Break. Poi c'è la fine, poi c'è il kick-off e poi ci sono... Speriamo che resista un po' di gente.
Sì.
Dove ci stanno?
Ok.
Intanto la
Chiudo.
Quanto tempo ci danno? Un quarto d'ora, 20 minuti? Sì, io posso stare tra un quarto d'ora e 20 minuti, così si sta in ritardo.
se va
Un po' più stretto.
Io la apro pure. Prova, Ah, sta pure le cose. Hackathon. Vabbè, lo metto così. Invece più un coffee o qualcosa.